So first of all, good morning, everybody, and thank you for having me. The main subject of this talk is about metaheuristic optimization of neural networks and deep learning architectures. But I want to mention a caveat straight away. That is, my initial goal was to give you a comprehensive picture on the progress of metaheuristic algorithms in training neural networks and optimizing their structure. But given the time available, also the fact that I want to show you a new library for Python that we developed, which I think is worth to be shown. I also want to show you how to use it. I ended up resizing a little bit the content devoted to this subject to make room for the other things. In the spirit of the conference, I tried to make an hands-on presentation with some notebooks. First of all, I will start with an introduction on metaheuristic algorithm and their common underlying ideas. Then I will try to talk about the optimization of neural networks and all the different components involved. And I will mainly focus on the optimization of the weights, as we will see later. And then I will introduce a new library for metaheuristic optimization called EvoMIP. And in addition to this, the plan is to show you a few notebooks available on Binder. You can find the link down the talk. And I will try to cover with those notebooks all the different topics dealt with this presentation. Okay, now, first of all, if you in Scopus, Google Scholar, Web of Knowledge, whatever you like, try to look for keywords such as metaheuristic algorithm, things like that, you will get a chart like this. And this chart shows how the interest, as well as the literature on this subject, has steadily grown in the last, I want to move this one, okay, has grown in the last decade. And this trend is actually driven by the new possibility that this family of algorithm, of technique, has opened, especially for what concerns the optimization of neural networks. Now, what do we mean with the metaheuristic algorithm? Now, the term, the word was proposed, the name was proposed by Fred Glover in 1986, and originates from the word heuristic, which you know denotes algorithm with a stochastic component. And then the term meta, which here means beyond. So in other words, metaheuristic algorithm means something like an overpowered heuristic algorithm, it actually is. Now, at the beginning, you know, the ideas behind these algorithms were quite original and based on the observation of natural phenomena. But you know what happened? Over the years, this got out of hand, and we started seeing a proliferation of ideas, many of them far from being original, which were just loosely inspired to things such, I don't know, the behavior of nearly every species of animal, you know, musicians placed together, gravity, entropy, you name it. But regardless this proliferation of technique, they have a common foundation. So they are all iterative algorithms, and they are based on a population of agents. Now, these agents move and interact according to the specific rules of the algorithm, with the goal of having efficient exploration and exploitation of the search space. Now, you know, the exploration is about to make sure that all the region of the search space are evaluated. The exploitation is when you identify a region which is promising, and then the exploitation is to be able to make sure that you are able to find the minimum there. Here we see an example of a metaheuristic algorithm in action. In this example, we want to find the minimum of this function. This is a pretty famous function for, it's a benchmark function for optimization algorithms. It's the two-dimensional Ackley function, which, as you can see, has a lot of local minima. And the global minimum is located here at the center for x and y equal to equal to 0. Sorry. The plot in the middle shows a population of agents randomly generated in the search space at the beginning of the algorithm, say at iteration 0. Now, the Metaheuristic algorithm, in this case, it's a particle swarm algorithm, which is pretty popular. What does? It moves this population according to some rules which are not relevant here. And as you can see, at iteration 30, you see we have a cluster of agents close to the global minimum, and at least one of them is very, very close to the actual global minimum. Of course, the larger is the population and the larger is the number of iterations, the closer you get to the global minimum. The drawback of this is, of course, the computation time, the computational time. One thing which is important to mention here, in case you are not familiar with this family of algorithms, it's that because of their heuristic nature, Metaheuristic algorithm can never guarantee to converge to a global minimum, not even for convex functions. So we can get very, very close, but there is no guarantee that we converge to the global minimum. On the other hand, on the other side of the spectrum of optimization algorithm, we have traditional techniques based on the calculation of the gradient of the objective function. This list is long, and I just reported some of the most popular algorithms, such as gradient descent, backpropagation, Adam, conjugate gradient. They are actually very, very popular because, for example, if you think about the optimization, the learning algorithm that people use for optimizing the weights in a neural network, it's usually backpropagation or Adam or conjugate gradient. And of course, there are reasons behind this popularity. For example, they are very, very efficient for convex functions. But on the other hand, they are sensitive to the choice of the initial point, the point where you start. They are sensitive to the step size. They are sensitive also to the noise in presence of an objective function with noise. Moreover, they tend to be stuck in local minima. And that's why, you know, over the years, variants with a stochastic component like the stochastic gradient descent were proposed to mitigate this effect here. Now, to make these drawbacks more clear, I prepared a notebook where you can test how the gradient descent behaves against the two-dimensional Ackley function, which I introduced before. I will show you the notebook in a second, but I won't spend time on that because the time is limited, and this goes maybe a little bit beyond the goal of the talk. Later, I will show you how a Metaheuristic algorithm can take all the two-dimensional Ackley function. So let's go to the notebook here. This is the notebook you can play with. So I defined the two-dimensional Ackley function. I also computed derivatives because it's necessary for the gradient descent. Here we can see the function in the range between -4 and +4 on both x and y. Here I implemented the gradient descent, and you can play with those numbers here, with the learning rate, with the number of iteration, and with the starting position. And what you will find, for example, in this case here, you see the gradient descent did not converge to the global minimum, but it was stuck here in this local minimum. This is something which happens, and you can see by changing the numbers by yourself that sometimes you are able to get to the global minimum, sometimes you are not. Now, in this case, you know where the global minimum is because you are seeing the objective function. But in those cases where you don't have access to this information, the strong dependence on the starting position is something which we are not happy about. So let's go back. Let's go back to the slides. Now, to introduce the subject of optimization of neural networks, Let me consider a simple case that is the architecture of a feed-forward neural network. Say that we choose the node with index I. From a mathematical point of view, mathematically, the output of the node Y is computed by this formula here, where N is the number of incoming connection, Z is the input, W is the weight, and B is the bias. Of course, phi is the activation function, sorry. Now, once we choose the structure of the neural network, and of course also the activation function, the output of the whole network, here denoted with hat Y, the output of the whole neural network is a function of the input layer X and the weights. So thanks to this, we can formulate the training of a neural network as an optimization problem. Okay. It's important to mention that the optimization of a neural network goes beyond the optimization of the weights. First of all, we have the optimization of the architecture, which means the number of layers, the number of nodes, the way we connect them. And then we have options for different things. So, for example, we have several options for the activation functions. We have options for the learning environment, for example, supervised, semi-supervised, reinforced learning, unsupervised, so on. We have many, many options for the learning algorithm. And finally, we have the optimization of the weights. But you know what? In many cases, and I must say, especially in our field, the optimization of the weight is almost the only thing which is optimized when we deal with neural networks. Because, you know, sometimes the architecture of the network is chosen by feeling in the best case, or feeling experience in the best case, by guessing in the worst case, and eventually it's changed just if, you know, the training doesn't go very, very well. It's not very successful. Talking about the optimization of the weights in a supervised learning approach, what we want to do is to minimize the difference between the output that we would like to get from the network and the actual output of the network. And this difference, this distance between what we want and what we get is measured by what we call cost function. In case of classification problems, you know, this function could be cross entropy, accuracy, misclassification rate, and so on. In case of regression, could be squared error loss, mean squared error, and so on. For gradient-based learning algorithm, it's common that weights are updated iteratively using the delta rule. And for example, if we choose the backpropagation as a learning algorithm, which is quite a common choice, now the backpropagation, probably you already know it, it's a first order gradient descent where the error computed at the output layer is propagated back to the hidden layer. Okay, if we choose the backpropagation, so this is the way we update the weights. Alpha and eta. Eta is the learning rate, alpha is the momentum factor. On the other hand, if we choose a metaheuristic approach, there is a big difference because the weights at iteration t cannot be computed from the weights at iteration t minus 1 because of the heuristic nature of the algorithm. Instead, the weight at iteration t is another thing. Is simply the values as far as we know at iteration t, which gives the best cost. So the minimum value for the cost function. Now, as you will see, I will show you an example at the end of this talk. This approach can be very convenient in several cases. But before before talking about in practice about metaheuristic optimization, I want to present you a new library for Python that we developed. This library, this package is called EvoMIP, and it is a library for metaheuristic optimization based on a library that we wrote a couple of years ago for R, which is called Emire. It's quite popular there. Now, it may sound strange that this package was initially implemented in R, because it's not very popular in our community, but if you are interested or involved in statistics, as I am, there R is very popular, and I still believe that it has a small edge, even though Python is catching up. But this is just a personal opinion that. EvoMIP includes 12 of the most popular population-based metaheuristic algorithms, including genetic algorithm, particle swarm, simulating annealing. Now, you may wonder, why another library for metaheuristic optimization? In other words, aren't there other options already available? The answer is yes, but EvoMIP can offer something more. First of all, unlike alternatives, EvoMIP can be used not only for unconstrained problems, optimization problems, but also for problems subjected to inequality constraints. Moreover, it can also be used for integer and mixed integer optimization problems. And finally, it offers a very efficient implementation of the algorithm that we include in the package. And in many cases, the user doesn't need to tune any parameters of the algorithm. So the default value that we put there for each algorithm comes from a set of studies that we perform. We checked several problems, optimization problems from literature, and then we chose the parameters that behaves better in this set of problems. Okay. So let's see how it works. So the workflow, it's like this. So the user defines the objective function, and then the set of parameters this objective function depends on. This set of parameters define what we call a search space. Once we have the search space, we define the population of agents which will explore and exploit this search space. And finally, we choose the algorithm we want to use for this minimization of the objective function in the search space. Once we choose the algorithm, we call the minimize method. Now, let's move to a notebook because it's easier to show you than explain it. Okay, let's start with this case here. Here is an unconstrained optimization problem. This is the two-dimensional Ackley function that we defined before. So, okay, this is some includes. Let me run so that we can use it. We can see it online, the results. Okay, I define the objective function, which is a two-dimensional Ackley function. And you see, here I define the parameters. The Ackley function is a two-dimensional function, which depends on, let's say, x0 and x1. You see, I define the parameters. So the first one, I call it x0, and the range is -4 + 4. The second one, I call it x1, and the range -4 + 4. And P is just the list of parameters. Now, one thing, you may say, okay, this is fine as long as you have a few parameters. But what about the optimization of the weights of a neural network when you have hundreds, if not thousands, of parameters? It's pity to define for each of them the corresponding parameter object. In this case, we have this function here. Look, this function here creates a list of parameters. So you need to provide the prefix so that we can have x0, x1, x2, and so on, whatever prefix you like, the number of parameters to generate, and of course, the range. This returns a list of parameters. In this p halt and p are basically the same thing. Indeed, if I execute, you see, the printout are the same. So in this way, we can define very quickly many parameters. Now, once we define this list of parameters, we pass to this class search space to define this search space. Now, you may wonder why to have a class for this, because as we will see later, the search space can also take into account the constraint. Now, this is an unconstrained optimization problem. Later, I will show you a constraint optimization problem. Okay. Once I define the search space, here just a configuration to say how many iterations I want to do. Here there are several other parameters you can set, but for now it's fine not to go too much in detail. Let's go on. So we execute. Here, the population. The population here, I want a population of 200 agents. Here, the constructor is the number of agents, the objective function, which I defined above here, the search space, and this configuration class, which basically tells how many iterations and other options, which here are not relevant. And once I have the population, I can use whatever algorithm I like. So here, for example, I choose the BAT algorithm. I can, if I want to use another one, just I change here buttons and use, for example, in the next example, the whale optimization algorithm, whatever. The construction is always the same. One thing, the population is the only required argument. This is basically the definition of this class BAT here. You see, this is the only required parameters because the other ones have a default value. Now, this is what I was talking about before, the fact that each Metaheuristic algorithm has its own tunable parameters for performance, of course. Now, we set default values coming from an optimization problem. So if the user doesn't have an idea about what this algorithm does, it doesn't need to change anything. So those parameters works out of the box. Of course, for complex optimization problems, you can help the algorithm by changing those parameters, of course. Okay, let's execute this. And then to perform the minimization, just call the minimize method. And here we have the summary. Let's see. Let's run. It's very fast, as you can see. And as I told you, the global minimum is at the position 0, 0. And you can see we went very close. Here we used the algorithm. This is the number of iterations, the population size, and those two parameters are not relevant here because this is an unconstrained optimization problem. I will explain them in the next notebook, this one. I'm seeing that I'm already a little bit late. So here I won't execute this code because it takes more time, because this is a very hard problem. This is well known from literature. So this is a constraint optimization problem. So we want to minimize this function here, which is a function in 4 dimensions, subject to this constraint. Just an important note, in EvoMIP, the constraints should be in canonical form, which means, in simple words, on the right-hand side, it should be 0. Okay, it's not necessary that is less equal or it could be whatever you like, but the right-hand side should be 0. This is a complex problem also because, you know, the variable x1 and x2 are basically the product of this term here, 0.0625, times another variable, x1 star, where x1 star is integer. The best value for this problem comes from literature, Lee and Gim, and this is the value. So I define the objective function and the constraint. For the constraint, we need to initialize this class here, which basically we pass the function and indication on whether it's less equal, greater, whatever it is. So you see the difference here is that in the search space, now we pass the list of parameters and the list of constraints. One last note about here. Here, the parameter x1 star and x2 star are integer, and this is specified by passing this through Boolean here. So by default, it's false. So it means that it's not integer constrained. Here, I set it through, so it's integer. And you know, when you execute the code, I want, because it takes a couple of minutes, you get this. You see the parameter is integer now, and it's specified here. And we get a value which is just in 2 minutes, which is very close to this one. Okay, before showing you the last example, I want to introduce this last example, which is basically maybe the most interesting one. The last example I want to present to you is basically the most relevant to the talk, I would say. That is how to use EvoMIP for the optimization of the weights of a neural network. Now, the example that I chose seems easy, but it's actually tricky. So assume that you want to train a neural network to generate 3 integers numbers, A, B, C, such as A is not negative, B is not positive, and C is equal to 0. Now, there are several approaches to tackle this problem here. For example, one approach could be, I use a generative adversarial network, which, as you may know, is a system of 2 networks contest each other in a form of sum zero game, zero-sum game, so zero-sum game. In other words, the generator generates some fake data. The discriminator compares this fake data coming from the generator with a set of good data that we provided. And on the basis of the feedback given from the discriminator, the generator, the weights of the generator are updated until, the generated data, the fake data, are so close to the good ones that the discriminator fails to distinguish them. Now, this approach has 2 drawbacks in general. One is that we need to generate a large sample of good data. Now, in this particular case, this is trivial. I generate a large sample of vectors like this. But, in general, this is not a simple requirement. The other problem with this approach is that the training of this kind of networks is very tricky. And usually it's very slow. But if you think about, we don't really need the discriminator for this problem. For example, I can give a feedback to the generator with an objective function like this. So I get the output, the prediction from the generator, so the output of the generator, and I check whether, those numbers A, B, C are what I like. And if I like, I return 0. And if I don't like, I return, for example, a number greater than 0. And the larger is the discrepancy from what I expect, the larger is the cost. Sorry?
We're running out of time, so I know this.
Okay, I will show you then. Okay. The problem with this objective function is that you cannot use it with the gradient-based approach. If you try to use it with Adam, TensorFlow will complain because this is not differentiable. Okay, so I prepared a notebook. Okay, it's late. You can play with it, but just to show you that with EvoMIP we are able to use this objective function here. And as you can see, we obtain an accuracy of 100% in generated these numbers here. Of course, I don't have time to go through the code because it's really late. Sorry if I went long.
Okay, thanks. Yeah, so we any questions for David on this talk? Does anyone have any ways that you want to use this library? Questions about how to use it?
Yeah, this would have deserved quite a bit more time. So maybe just suggesting to continue the discussions on Slack, and particularly also you didn't discuss much about the Python package itself. but
Yeah.
you could have mentioned a bit.
Yeah, I realized that the time was too short for presenting a new library, also because, you know, you need to see it in action. You need to understand the potential of the library. I understand that the time is not enough. But in case somebody got curious about that, we can interact offline about that.
It's interesting stuff for sure. Yeah, thanks.
Yeah. In fact, I'll ask my question on Slack. So